Hello, good morning, good evening, good afternoon, everybody, wherever it might be. Well, today we host a seminar from CISA, from Trieste, Italy. And our speaker is Francesco D'Andrea from the University of Naples. And he paid us a visit here at CISA so that he can revisit Vaksman-Soibelman old quantum spheres and complex quantum projective spaces. Francesco, the floor is yours, the Zoom is yours. Take it away.
Okay, thank you, Piotr. Okay, so thanks everybody for being here. As Piotr said, I want to say something about these quantum sphere and projective spaces. So let me start with a very brief history of these spheres. So I would say that the first example is, of course, SUQ2, which is a quantum trisphere. And I'm not sure, usually I cite a paper by Voronovich in 1980s. There is also one in 1987. The first one is about pseudo groups. So the second one has SUQ2 in the title. So you can choose which one is the date SUQ2 was invented. There were also a lot of other people working on this subject. There are papers by Drinfeld and Jimbo in 86, Padev in this pool in 87. Also Manin, I think his first paper is in 87, so okay, a lot of people working on this stuff. But very interested in the approach with the sister algebras, so Voronovich approach. So a bit later in the 90s, actually in 1990 exactly, Vaksman and Soibelman introduced the other dimensional quantum spheres as homogeneous spaces, quantum homogeneous spaces for quantum unitary groups. So here Q is a deformation parameter, and so is a number, is a positive real number. When Q is equal to 1, you get an ordinary sphere. And this that you see on the screen is the notation that I use for the sphere. N is a natural number including 0, be 0. And this is the S2n plus 1Q, where 2n plus 1 is the dimension. What we think is the dimension of this quantum. Okay, from the definition, I will recall the definition. This is described by some associative algebra, which I will present later. And one can see from the definition of this algebra, I mean, it's very easy that if you replace Q by Q2 minus 1, you get isomorphic. So this is the first kind of symmetry in this family of spheres that is immediate from the definition. Okay, so in 97, there is another important contribution by Albert Shaw, which I don't know if he's online, but he didn't join probably. Okay, he constructed explicitly a groupoid, which depends on the dimension, but does not depend on Q. And the convolution algebra of this groupoid is exactly the C-star algebra of S2n plus 1Q, where the one on the left is the C-star enveloping algebra of the one that I denoted by curly A before. So in this paper...
Question, so those are isomorphic as the sister algebras, yes?
As the sister algebras, yes. And the first two, the one with curly A as algebras, as a star algebras. Okay. And unital, these are unital, so the isomorphisms and the unit into the unit.
But to make sense out of this, you have to add that this is given as polynomial algebras in the original generators.
Yeah, but I will tell what it is. It's just some quotient of an algebra of non-commutative polynomials by some relationships. But I will record. The curly A algebra is dense inside the sister algebra by construction. And so what Shaw did was to construct a groupoid depending on n on the dimension. Was convolution algebra is the sister algebra of this other dimensional sphere. In his paper, Q is bigger than 1, while Q equal to 1, that is the ordinary sphere, so you have commutative sister algebra. And here Q is greater than 1, but with the symmetry that you have Q going to Q to the minus 1, this includes also every Q greater than 0 and different from 1.
But sorry, was it clear from the beginning that this sister algebra should be isomorphic to any sister algebra of any groupoid?
Well, I don't know, but here in this paper is explicit. I mean, the isomorphism is explicitly constructed. I don't know if it was clear, but basically, I mean, very few sister algebras are not convolution algebras. I mean, it's not that easy to find examples. I mean, there should be a groupoid. It was almost sure that there was an underlying group point. But it is not just any group point, it's explicit, it's a lot of properties, it's amenable. I will tell you what the group point is.
If I might,
It's entirely, yeah.
Adam, look, this was highly non-obvious that these sister algebras are graph sister algebras. It was a big discovery of Paul von Szymański.
Yeah.
And now once they are graph sister algebras, we have a natural way to view them as groupoid sister algebras. But
Yeah.
even that this groupoid that we have for sister algebras, graph sister algebras, is the same as the original groupoid of Schur, is non-evident.
Yeah, but
This
this is the next.
So
Yes.
not only the fact that this groupoid does not depend from Q, but and also this graph, but even the fact that it is isomorphic to any sister algebra of some graph, even this is remarkable.
Yeah, that was not obvious at all, but it was an alternative way of proving that it's Q independent as a system.
Yeah.
Yeah,
The independence on Q is not obvious. That it was a convolution algebra, I mean, you could bet it because, as I said, if you take the sister algebra, unless it's very pathological, usually is convolution algebra. Okay, so the next contribution was by Young and Szymański in 2002. They construct a graph, again, depending on the dimension, but not on Q, such that this sister algebra that now we know that doesn't depend on Q is isomorphic to the graph sister algebra of this graph that I did not by here. But this is not original notation, but I use it because the original notation was a capital L, but for me L is L bar, so I changed the letter. So here in this paper, Q is between 0 and 1, but now 0 is included. This was not included in previous paper, and now 0 is included. You have to be careful when you define these algebras for P equal to 0, but you can do it, and still is independent of Q. Okay, so these are not a random example. These spheres, I would say that a lot of people worked on these examples. You can see that the original paper has a lot of citations. And here I'm listing only a few names, random names of people that I know that worked on this. I am sure that I missed a lot of people. I already see that Elmar is not in the list.
But he's on Zoom.
Yeah, so sorry, Elmar. I missed your name, but there are really a lot of people who worked and are still working on this quantum sphere and on the yeah, and on the corresponding quotient by U1, which is what we call quantum projective spaces. Okay, so the first paper was 35 years ago. What can we say new about these examples after 35 years? Well, I want to just mention something that is not related to the talk. It's something that does not involve me, but just to say that there are still many groups working on this. So something very recent is what this group did. The first two names I should not try to pronounce them, probably. So Jens, yeah. Okay, but you can read the names. And these recent activities, very recent, is like last 2 years, is I would say last paper is in 2024, is this year, is about a study of these sister algebras from the point of view of the reference theory of compact quantum metric spaces, and then convergence when you take, for example, limits when you vary Q and so on and so on. Okay, so there are still people, there are still many things to do actually with these sister algebras, and what is that I'm going to talk about today.
Sorry, quick question. What do you mean by
Yes.
hard state on SQ? This is not a quantum group, or is it?
The restriction of the hard state of quantum unitary groups to this sphere that is a subalgebra, is a sister subalgebra.
Just restriction. It's a homogeneous space.
Okay.
Yeah.
Okay. So I would like to mention 3 things. I mean, probably, yeah, if there is time, 3, otherwise 2, or worst case 1, depending on how interesting is the first point. So the first point is this fact that we know that the sister algebra of a quantum sphere depends on Q. And I mean, it was clear that the polynomial algebra was not independent on Q on the other end. I could not find any proof of this, so I just wrote down the proof recently. And so I would like just to spend not a lot of time. I have just a couple of slides about this to sketch the proof, just to get some feedback about this. So the geometrical interpretation is that this family of spheres that depend on Q on this parameter, they are all isomorphic as non-commutative topological spaces. The sister algebra is the same, but not as non-commutative algebraic variables. Okay, so this is the first point. Second point, first point is about algebras. The second point is about sister algebras. So if you take the graph of Szymanski, there is an associated groupoid, which is the path groupoid, and the convolution algebra is the same as the graph sister algebra. And then you have also the groupoid introduced by Shaw. These two groupoids define the same sister algebra, they are isomorphic, but of course, this does not mean that the groupoids are isomorphic. And they look quite different. So another thing that I would like to mention is, okay, these are isomorphic indeed, and I would like just to say a few words about this isomorphism, not much. And the third point is the most mysterious, maybe the most interesting, and here, so let me see if I can say this in a different way. So concretely, what I want to talk about is for a family or for a next family of sister algebras, I would like to see if I can give a geometric reconstruction leading to star homomorphism from A tensor A to A, which when A is commutative, you can just take a multiplication map, but can we do something when A is not non-commutative? So in some sense, and we will see why, you could phrase this third point as I'm wondering for what family class of quantum spaces you have a kind of a diagram. I will talk about this at the end. So the third point is a bit more mysterious, but also I will try to spend more time on this because it is also more interesting. Okay, so part one, the polynomial. Let me give just a flash, a couple of relations in the definition of the algebra of our sphere that I denote by curly A. N is a non-negative integer, Q is any non-negative real number, it could be 0, and this algebra is generated by some elements that are denoted by zeta I and zeta I star. I goes from 0 to n, and so is the universal unital associative star algebra generated by these elements with some relations. You have quadratic relation, and I write only one. So for example, a relation saying that zeta 2, zeta 1 is Q, zeta 1, zeta 2. So you have this kind of commutation relation where they don't really commute the generators, but you get it. There is a list of other quadratic relations that I'm not writing. Some are easy, some are more complicated. And there is one relation which is not quadratic because it's also a constant term. And that you can interpret as saying that this is a kind of a condition on the radius of this object. It's a sphere of the radius 1. If you sum, multiply each generator by its star and the sum, you get it. Is a star algebra with obvious star involution, where zeta I star is the conjugated of zeta I, is the joint of zeta. Okay, next, let me recall the polynomial algebra of SQ2. For these, the generators I denote by alpha and beta. You put alpha, beta, alpha star, and beta star in a 2 times 2 matrix with a minus q here. You impose that this matrix is unitary, so multiply by this adjoint matrix in 2 possible ways. So impose that you get the identity matrix and you get the relations of this algebra. So you can write down these relations. Not a complicated.
Can I make a very quick remark? Because I think it's worthwhile to mention it, but if you look at the relations which you didn't write, so you have to imagine them, you see from these relations that one and only one of these generators is normal.
Yes.
And now if you set this normal generator to be self-adjoint, then you get the sister algebra of dimension quantum sphere.
Even dimensional.
Of even dimension, just one dimension.
Yes. But I don't care about the
yeah.
For me, only other dimensional spheres exist.
But they are also graph sister algebra.
Yeah. Okay. So there is a surjective star homomorphism from if n is at least 1. You have a subjective star homomorphism from the algebra of the sphere to the algebra of SQ2, which is very easy to write. Zeta 0 goes to alpha, zeta 1 to beta, and everything else goes to 0. And this is actually an isomorphism if n is equal to 1. Okay, this is all what you need to know about this. Okay, so next, a folklore theorem, as somebody calls it. And I have to start, let me start from a result
Determinant one condition is
Okay, yeah, that is automatic. If you write the matrix like this, the unitary implies special. So
And sorry, what was the question?
if you have to impose that the determinant is one, no, you don't have to. Just unitary implies that the Q determinant is one, if you want.
Okay, okay.
Okay, you get all of the relation just imposing unit of that. Okay, so this first theorem that you see was proved by Uli in 2008. So this is about the dependence. Here, what is used by C instead of purely A is, I mean, just different notation for the same kind of algebra, except that you have a two-sphere, which I did not mention. I didn't give the relation. And for these are the so-called published sphere that depend on two parameters. Besides Q, there is an extra parameter that here is noted S. And what he proved was that for a fixed Q, if you take the sphere with parameter S and the one with parameter S prime, these are isomorphic if and only if S is equal to S prime. So this is a kind of result in the direction I want to go. You have independence on the second parameter, but I guess that for us to, with the same proof, kind of proof, you can prove independence on the first parameter. So that was, I mean, when I was looking for a proof of this fact, that was the only paper I could find, and I still believe there is nothing else in the literature, but if you find something, please tell me. So then I decided to write down the proof of this theorem for odd dimensional spheres. You take any two integers n and m greater or equal than 1, any two deformations parameters q and q prime in 0, 1, including 0 and 1, then the algebras of s to n plus 1q and s to n plus 1q prime are isomorphic if and only if the dimension is the same and q is equal to q1. Okay, maybe this fact about the dimension, which must be the same, this is phrased in, I mean, I didn't care about this in the preprinted on archive. On archive, the dimension, I assume that it is the same, but the proof, I mean, you don't have to change the proof to prove this. I mean, what is interesting is that when they have the same dimension, they still depend on the definition. I try to sketch the main idea in one slide when the parameters are not 0 and not 1, because these are kind of singularities, but when the parameter is 1, is trivial because the algebra is commutative, and if these two algebras are isomorphic, and one is commutative, also the other must be commutative. So q equal to 1, there is nothing to prove. Q equal to 0, there is something to prove, but I'm excluding q equal to 0 because I have a wonderful proof that wouldn't fit in the margin of the next slide. So to put everything in one slide, q equal to 0 is excluded. But it's not very different, it's just a bit long. So then I was in Cortona in June at the conference when I put on archive this preprint, and I was talking with Robert that was at the conference, and he asked me, okay, but do you think it is possible to generalize these to arbitrary quantum spaces? And I said to him, okay, maybe it is possible, but I don't know, my proof is very specific for spheres. It looks like it is very difficult. And then he did it in a couple of months. In September, end of September, he published a preprint on archive. And in here, there is the proof when X is G over K. You take a Q deformation of this kind of homogeneous space. So you have some condition on G of K that if you want, you can read here. And you prove the same kind of theorem that there are two such deformations are isomorphic if and only if the deformation parameter is, well, they are either the same or one versus the other. Now in this theorem, q equal to 0 is excluded. I don't know if for what reason, but okay, we can ask Bob if he's online. Okay, so sketch of the proof. I want just to show in one slide the idea behind this proof so that you can tell me if it is very trivial or if you have any kind of feedback. Yeah,
Robert is not.
Okay, so n is greater or equal than 1 here. I take q prime less than q and both between 0 and 1. And I want to show that there is no surjective staromorphism from the quantum sphere S1 plus 1q to SU q prime. And they claim that if I prove this, then I'm done, because if you have an isomorphism between the algebra of two spheres, the second algebra, you can use your quotient map to the algebra of SQ2, and you get a surjective star homomorphism. So if this does not exist, the isomorphism does not exist. So this is what I want to show by contradiction. So this thing that does not exist, I call it phi, and I want to show that there is no phi. And just to simplify the notation, A is the first algebra and B is the second. So A is the sphere with the Q deformation parameter, B is SQ2, is actually Q prime as the deformation parameter.
Can you repeat this argument while you are done here?
So suppose you have isomorphism between the algebras of the spheres.
Okay,
The
the
second
same dimension,
sphere,
different Q, okay?
same dimension, different Q. No, same dimension doesn't matter. The second is 2m plus 1 dimension. The second has parameter Q prime, and I have surjective star homomorphism on SU Q prime 2. If there is an
When you say
isomorphism,
SQ prime 2, you mean just polynomial algebra, right?
polynomial algebra, yes. So if I have an isomorphism between sphere where the second has any dimension, then I also have a surjection to SQ prime 2 because I just compose.
Yes.
But here Q and Q prime are different. So I want to show that this you can have only if Q are equal to Q prime. So for Q prime less than Q, you don't have. So how do you do it? You have your generators alpha and beta. You can construct a basis of SQ prime 2 given by alpha to the power j, beta k, beta star L, and its adjoint. And if you take the monomials with k plus L greater or equal than some m, this span a subspace that I call Vm here. This is a subspace of B, the algebra of SQ prime 2. Next, you show that you have a descending filtration by ideals. So B0 is B, V1 is inside, V2 is inside V1. Each one is a two-sided star ideal in the one before, and the intersection is 0 because you get greater and greater. Here are the inequalities with the bigger and bigger m, the intersection, only the 0 polynomials. Okay, then you call I the ideal in the algebra of the sphere generated by commutators. You study this ideal, and by studying this ideal, you show that this map phi, which does not exist, if it exists, it should map zeta 0 to lambda alpha plus x or to lambda alpha star plus x, where lambda is a unit complex number and x is in V1, is in the first ideal. Okay. And then you use induction. Now is where you use commutation relations. So you show that you take all the other generators, zeta I, call yi the image of this generator zeta I. Zeta I is in the ideal E spanned by, generated by commutators. Then yi should be in V1. But using the commutation relation with Q and Q prime, you show that if yi is in Vm, then it should also be in the next ideal Vn plus 1 for every m greater or equal than 1. And then it's 0 because it's in the intersection of all this ideal and this 0. Okay, so all the zeta I except the zeta 0 are in the kernel of this map phi. So you get a surjective star homomorphism from the quotient A over I to B, but I is the ideal generated by commutators. The quotient is commutative. B is not commutative, and so this is the contradiction. So this is the idea of the proof. Well, it is not very difficult, but okay. You have to think about it.
Why is the intersection of all these ideals 0?
Well, because an element is in Vm only if it has non-zero coefficients multiplying a monomial with k plus L greater or equal than m. When m becomes bigger and bigger, so all of the monomials less than m should have 0 coefficient. When m goes to infinity, it means that all coefficients in this basis are 0. Okay. This is the linear basis of this B as a complex vector space. Okay, so let me just check what I see. Okay, actually I went quite fast. So let's go to more interesting things. C-star algebras. So I have to recall.
Excuse me. You pointed out to the case of Q equal to 0. You said that you have a small proof, a short proof for the case of Q.
No, I was joking. For Q equal to 0 is the same proof. You have only to, is only a bit longer to explain it because this basis, this Vm, this basis of SQ prime 2 is a basis only if Q prime is not 0. So if Q prime is 0, you have to change it a little bit, but not much. It's only longer to explain. It's not more difficult.
That's a PPW basis.
Yes, however, for Q equal to 0, we have a commutative space, and this is a results in algebraic topology that two different spheres are not homeomorphism.
No, I
That-
think that for Q equal to 1, you have something commutative. For 0, no.
Zero is
Yes. For Q equal to 1, yes. I'm sorry.
Yeah, okay. But Q equal to 0, really, I mean,
I'm sorry. Yes.
I just wanted to fit everything in one slide, but it is the same proof. You just have a few lines more to explain how you fix Q equal to 0.
And
Okay, so graph sister algebra
also-
again.
Sorry, also for Q equal to 0, Q is no longer a quantum group, yes? It's only a sister algebra.
Yeah,
but
no,
okay.
the trick is that for here Q prime is less than Q, and this works when they are both non-zero. When they are 0, I choose to be 0 the second. I can take Q equal to 0 and the target non-zero, and I do the proof in this direction. So it's just more difficult to explain, but it's not really, there is nothing more than what I wrote. So
Yeah.
Q on the left is 0, on the right is not, and still the same thing. If one carefully checks all the details, it still works. Okay. So, but the preprint is on archive, so if you want to check the proof and if you find any mistake, you can write me. I will be very happy, or observation or that. So, graph sister algebras. A graph for me is just a set. Countable set is 0 of vertices, a countable set is 1 of edges, and two maps, source and range maps that tell you for every arrow what is the source and what is the range. And you can see the picture of what I mean by
So what sister algebra space?
well, this I don't know. This is a good exercise, but probably nothing is. There is a quantum for sphere plus some arrows, no, or maybe minus some arrows. Okay, so let me recall you that if a vertex like this here emits no edges, then it's called a sink. So this is an example of sink. An infinite emitters is when you have infinitely many outgoing edges, and the graph is refined. You don't have any infinite emitters. Also, if source and target of an edge like this here are the same, this is called
Why do you assume countability?
because it is in the paper of past and others. I don't know if they really need it, but okay. So actually, then in example, I assume much more because it's always finite sets. So it doesn't. And maybe I should not read the whole definition of graph sister algebra, but to any graph you can associate in a standard way, I mean in a canonical way, a sister algebra denoted by C star of E. It is
So
the graph.
spoiler alert for you. That's what we are going to do in the course.
So this is sister algebra. What is important, let's forget about the exact definition. What is important is that it is generated by a set of orthogonal projections. Here is a PV, then they are denoted by PV, where P is a vertex. For each vertex, you have a projection, and they are orthogonal. For each edge, like this here, you have a partial isometry, and then there are some relations that are encoded in the graph. For example, I read only one relation. For every edge E, SE star SE, where SE star is the adjoint, is the projection of the vertex, which is the range of the edge. So you have these relations that are encoded in this. And then, okay, this is not really a definition because actually you have to show this is defined as universal sister algebra in a suitable sense. You have to prove that it exists, and you prove that it is a unique in a suitable sense. But I'm not going to talk about this because
Sorry, Francesco, is it obvious that SF star SE is 0 and F is different from E?
mutually orthogonal also refers to partial isometries. And this is something that I'm not sure. I mean, I usually put partial isometries with orthogonal ranges
That's
in the
what I'll
definition.
put, yes.
But I think that if you have Rofinite, you can prove it.
Yes,
You don't have to
and we will
assume.
do it in the
Yeah,
class.
in general, you have to. So here, mutually orthogonal means also the isometries.
Then I'm happy.
Okay. Okay, so now if you have a graph sister algebra, you have also an action of U1, which we call the gauge action, and this is defined in a very simple way. T is in U1, the action that I denote by gamma, the action, because alpha is the generator of SQ2.
So it's gamma.
No.
Alpha, alpha, beta,
Yeah.
sorry.
So gamma T on so projections, these generators, projections are invariant under these one actions, and the partial isometries they transform according to this rule. Gamma T of SE is TST. Okay, so this is the definition of the gauge action. You can prove that it extends, it is well defined. It gives you a continuous actions by automorphism on the graph sister algebra. And you can show that the graph sister algebra decomposes as a complex vector space as a direct sum over all k in zeta of some Lk. Well, not really direct sum. There is a completion. You have to close this direct sum, where Lk is the set of elements that transform like this under the gauge action. Gamma t of A is equal to t to the power k times k. If A satisfies this condition for all t in U1, then it belongs to Lk. It is the definition of this vector space. And this gives you a zeta grading on this algebra. Okay, then okay, I thought I wrote in the slide what it means to be strongly zeta graded. Doesn't matter. There is a notion which is for a graded algebra. There is a notion of a strong zeta grading, which from our point of view is equivalent to saying that if you take the subalgebra of invariant elements under U1, the inclusion is a Galois extension. And for graph sister algebras, there is a theorem that tells you when it is strongly zeta graded. One condition sufficient, not necessarily, is that E is finite and with no sinks. There is a necessary and sufficient condition that I'm not writing because it's too complicated. I mean, it's not complicated, but it's long. The important thing is that if you want also the sister algebra to be unital, then unital and strongly Z-graded this happens if and only if E is finite with the sinks. So that's why I'm mainly interested in finite graphs without sinks. Okay, so of this Lk, L0 is particularly important. L0 is just the set of elements in the algebra that are invariant under the gauge action. This is a sister subalgebra. It is called the core of the graph sister algebra, and it is an inductive limit of finite dimensional sister. So this is an AF algebra. Well, this is true if E is rho finite. I don't know more generally you can say something about it. I don't think, of course, that is always true. If E is rho finite, this is true, it is in Reborn book.
Sorry, Adam, you want to ask a question?
Yes, I'm not so sure that in this theorem, the second condition is the same in those two bullets, yes? E is finite and with no sinks. But
Yeah,
one is only a sufficient condition, and the second one is
sufficient for strong grading. Is sufficient for strong grading. Is also necessary if you want a strong grading and the unital system.
So this is correct.
Yeah.
Okay.
But if you don't care about unital sister algebras, okay, that is only sufficient. It's sufficient because it gives you a strongly graded unital sister algebras. You also have strongly graded non-unital graph sister algebras. And for those, the condition is a bit more complicated. So the phrasing maybe is not optimal, it's a bit confusing, but you can read the second line, and the second line is what is really important, because we care about compact quantum spaces, unital sister algebras, and then there is no escape. If you want strong grading, you need finite with no sinks.
I mean, right to left implication you have always, but left to right you need this unitality.
Yeah. Okay. So yeah. So L0 is what we call the core. AF core is rho finite because it's in AF algebra, and LK in general is what we interpret as some kind of a bimodal of sections of a line bundle on the quantum space, which is described by this. So L0 is a sister algebra. It is a dual to some kind of compact quantum space. On this quantum space, a line bundle from a dual point of view are given by these sections. Not all of them, but it's given. Okay. Let me give examples. First example is this graph with two vertices and three arrows that you can see the picture here. This is the graph of S3Q, which is also SUQ2. You can look at the AF core. The AF core is SU2 over U1. It's a deformation of CP1. Is what we call CP1Q, we denote by CP1Q. Also called usually is the standard Polish quantum sphere. And this is an AF algebra, so it is inductively, in fact, you can write explicitly as the closure of a union of subalgebras, where these subalgebras, each AK is a subalgebra, and they are one inside the other. AK is inside AK plus 1. Well, you can even write the Bratelli diagram of this AF algebra. It's not very difficult. I don't know if I could spend too much time on this.
You are doing fine.
Okay, so this is the Bratelli diagram. This you can find, I mean, given the graph, you can construct the Bratelli diagram by looking at the proof in Reborn book that the core is AF. And in this proof, you can really see what are these subalgebras and what are the inclusions. So how do I get this diagram from the one on top? Each column has two vertices because these are the two vertices of the graph of SU2. Each column tells me, so the third column tells me who is the algebra A3. Each vertex is a factor. A3 is a sum of matrix algebra. Each vertex is a matrix algebra, it's a full matrix algebra. From the arrows, so the first vertex is always C, is the subalgebra of scalars proportional to the unit element. And the arrows telling me, from the arrows, I can deduce what are all the other algebras and what is their dimension. Because here there are single arrows, it means that this C embeds with multiplicity 1 in this algebra and this algebra, so these two are also C. Then here I have only one incoming arrow, so this C embeds here with multiplicity 1. This is also C, one dimensional, but this is two dimensional because I have embedding on the diagonal of two complex numbers here. So this is 2 times 2 matrix. This is still C and 3 times 3 matrices and so on. So this vertex, for example, is a matrix. Okay, this is the diagram that you read from here, basically. You put each column has two vertices, and from one column to the next, you write an arrow from a vertex to the other, only if there is a corresponding arrow on the diagram of the graph C-star algebra, say, of C-star of it. Okay, I wanted to show this picture only because it's very similar to the next example, very similar but very different. I mean, it looks similar, but it has very different properties. So this is C-star algebra. We know that, for example, if you look at the row below, this is an hereditary and saturated subset, which means that this algebra, C-star algebra, is not simple. In fact, you can take a quotient. In the kernel, you have compact operators. These are compact operators. And the quotient is just a C, which is the C that you have on top. Okay, so what is the next example? The next example is this C-star algebra here, with the two vertices which I denote by 0 and 1. Okay, it's not very different from the one we had before. In particular, the F-core doesn't look very different, but it is. So now if you write the Bratelli diagram of the F-core, still you have one vertex, which is the root of this diagram. Then you have in each column two vertices, 0 and 1. And if I'm at 0, at a vertex 0, I can go from 0, I can move to 1, or I can stay at 0. So I can go here or I can go below. But if I am at 1, I cannot stay at 1 because there is no loop here. I have to go at 0. So from 1, I needed to go necessarily here. 1 is below, and I have to go to the vertex 0. So in this diagram, I denote by 0 and 1 edges instead of vertices, because then if you compute, so this is the Bratelli diagram of this AF algebra. We know that this is a convolution algebra of a groupoid, and the groupoid is constructed with right infinite paths in this diagram. And the right infinite paths, what are right infinite paths in this diagram? But just the sequences of 0 and 1, where every one is followed by a 0. So what is this C-star algebra? Maybe before showing, I should have asked the question to the audience. They could have guessed. So this is the AF algebra of the space parametrizing Penrose styles. It means that it's the same as the convolution algebra of the groupoid, the relation, where the set is binary sequences where each one is followed by 0, and the relation is the relation of Taylor equivalence. So this is the same, these are isomorphic.
It's amazing that you reverse one arrow and you have a C-star algebra of one to real projective planes.
And this is nice because instead of describing this AF algebra by a complicated diagram or complicated equivalence relation, you can realize it as AFR of something with two vertices and three axes. So that is nice. Okay. And for those who are wondering what is a Penrose styling, I wanted to show a picture, and I said to somebody, this is just to show my latex skills. So there is really no other purpose, but it's very nice. I mean, for me, these tilings are hypnotic. I could watch them for hours. So this is called the cup wheel. Okay. Back to quantum spheres. So let's go back to the graph sister algebra of SQ2. So you can see again here the graph of SQ2. Vertices now are labeled as 1 and 2. And I denote by E infinity the set of right infinite paths in this graph. So what is the right infinite path here? What can you do? You can start at the vertex 1, make a number of loops around 1, maybe 0 or a number greater than 0. Then you go to 2, and you make infinitely many loops around the 2. Or you can do infinitely many loops around 1. You can start at 2, you can make infinitely many loops around 2. And that's all. There is not much more you can do. Sorry, not much more. There is nothing more you can do. So you can, there is a bijection. You can label each one of these right infinite paths by a natural number or infinity, where infinity is the path where you don't leave this loop. You do this loop infinitely many times. And the natural number identifies the path, which does, so say n, corresponds to the path that before reaching the vertex 2 has length n. So basically, you cut in this path, you cut the loops around the 2, it becomes finite. You look at the length, and this is the natural. Okay, here actually there is a topology. Well, the one on the right is the one-point compactification of natural number, and on the left.
Wait, an infinity you get for this going rather first.
You never reach 2. Infinity, you never reach 2. You do infinitely many loops. Okay. Now there is a topology on this infinity. And there is a topology such that then you can construct, this becomes the space of objects of a topological groupoid, the path groupoid of the graph. I don't want to say much about the path groupoid, but we are going in the direction, okay, I want to mention what is the relation between the path groupoid with the groupoid introduced. For the path groupoid, this E infinity is the space of objects with the correct topology. And in the case of show, remember that we are looking at the tree sphere now. The set of objects is n bar with this topology, 1.1. So what is the groupoid of show? I can tell what it is for in dimension 3 is not that complicated. So you take the zeta bar, 1-point compactification of the integers, where the extra point I call it plus infinity, because this tells me what is the action of zeta on zeta bar. So infinity is a fixed point for this action. Then you can form the action groupoid, zeta acting on zeta compactified. And this action groupoid, you can consider the reduction to this set of objects given by n compactified. This is what we call the Tetris groupoid of order 1.
And the action of z on zeta bar is just by shift.
Is by shift. You sum, and infinity is a fixed point. Anything you sum to plus infinity doesn't change it. Okay, so then you take the Cartesian product with zeta, which is a group, but is also a groupoid with one object. So you don't change the set of objects. In particular, the set of objects is still n bar. And inside here, you look at the following subgroupoid that I know by curly G. So the subgroupoid is given by all the morphisms. Now a morphism here is given by 3 integers, k0, k1, and 1, where the last one can be infinite. Well, this last one should be also non-negative. And in order for, by definition, how this reduction is defined, also the sum of k1 and m1 should be non-negative. Okay, but in any way, you have 3 integer numbers, and the last one can be infinite. If the last one is infinite, the sum of the first 2 should be 0. This is the condition that defines the morphisms in this subgroupoid. Okay, now this subgroupoid it was proved by Shaw that this subgroupoid, the convolution algebra, is the sister algebra of SQ2, and you can show that in fact this groupoid G is exactly the path groupoid of the graph that you see on top. I'm not going to do it because there are a lot of technicalities. The definition of topology on the set of arrows is subtle, on the set of objects less subtle, but still you have to give it. But at least you have an idea. Here you can see the map between objects, infinity that goes to M bar, which is the set of objects of the groupoid of Shaw. You can imagine how it works. Also for arrows, you have to count something in a suitable way. And then, okay, there is a lot of details about showing that this map is continuous, it has continuous inverse, and so on.
And you mentioned morphisms of subgroupoid. What do you mean by morphisms of?
No, okay, because I'm using morphism with two meanings. Morphism between groupoid and element of G1, elements of G1, the arrows.
Okay.
So here, by morphism, I mean the arrow in the group G. Sorry. Yeah, I should not use the same word for two.
Sorry, could you describe those spaces just topologically? For me, my feeling is that any natural candidate would be a Cantor set and nothing more. I don't have any idea what else could you get from such a construct.
So on infinity, you give an explicit definition of a neighborhood basis for any right infinite path. And the neighborhood basis is something which has the collection of all the paths that have an initial subpath equal to the one we are looking. And it's not very different on how you define a neighborhood basis for the Cantor set to think of it as a binary sequence. It's very similar. It's the same idea. So you have this kind of cylinder sets, and you get an ultrametric space. The topology is the topology of the ultrametric, and you have all the funny things. So it is the Cantor space in particular.
Okay, that's what I would expect. So you don't have any isolated point. You have a compact space which is infinite and zero dimensional. Yes.
Yeah. And
okay.
So yeah. So well, yeah. Here you can see the topology is the one of n bar. So plus infinity is not isolated. Yes.
Yes, here is different. Yes, it is.
The same topology is just in a different presentation. Okay, for higher dimensional spheres is more complicated because you don't have just a subgroupoid of the Toeplitz groupoid of order n that here. In the Toeplitz groupoid of order n, you replace zeta and zeta bar by zeta to the power n, and bar by n bar to the power n. The first zeta remains zeta, the group that you take the Cartesian product with. The reduction that you see here is the Toeplitz groupoid of order n. Then you take the Cartesian product by zeta. You have to consider a suitable subgroupoid, but then also a quotient. There is a relation, and you have to show that it makes sense to pass to the quotient. You get the groupoid. It's not that easy to describe the groupoid. It's even less easy to say what is, even at the level of objects, not of arrows. What is the relation, the isomorphism between the path groupoid of the graph of a sphere and the bar n bar to the power n, the set of objects of this subgroupoid of this subquotient. So I'm not going to do it. If you are interested, there is a preprint that I put this here online, but you can do.
I have a stupid question. I apologize. Somehow missed what you mean by writing this kind of restriction to n bar.
It means that you take the pairs of numbers k1 and 1, where n1 is not in zeta bar but in n bar.
Okay. So
and if I ask with zeta, I should not go out from n bar. So also the sum should be non-negative.
Okay.
And that is the reduction. You take a less objects, but all the arrows between these less objects. If you think of the groupoid as a
okay. Okay, thank you.
Okay, so it's the full subgroupoid induced by this subset of objects. Okay. So anyway, yeah, if somebody is interested to the general case, you can look at this pre-printed. The general idea is that you always have to count something. You transform a path or a pair of paths into a pair of numbers plus infinities. But then, okay, there is a lot of topology involved, quotients, subspaces, and so on. But everything is explicit. Okay, last example. So last example, I want to give one more example of a family of graph sister algebras. a family of graphs, I would say. So take any set S, any subset D of S, and any function F from D to S. Then you can define a graph by the following formulas. E0, the set of objects is S, is the big set. E1 is the set of pairs XY in D cross S, such that Y is the image of X. So this is the graph of the function. Okay, this is a graph, still is a directed graph where X is the source and Y is the target, and it has some special properties. It has the property that each vertex emits at most one. This is what is usually called a functional graph. A functional graph is any graph where each vertex emits at most one edge, and they are all of this form. They all come from a suitable.
Can it be that it meets no edges?
Yes. Okay. I mean, here S, the function is defined on D, which is a subset of vertices. So the function is everywhere defined. It is a function, but the domain is not the whole vertex set. It is D. Okay. So example: take the following two graphs, two arrows, one after the other, and these two parallel arrows. In both cases, the graph sister algebra is M+C, different matrices. The first one is a functional graph, and the second is not. So the only point of this example is to remind, as always, that you can use very different graphs to define the same, to get the same sister algebra. Different graphs with also very different properties. So it does not really make sense. You have a graph sister algebra, you have a sister algebra, which is a graph sister algebra, and say and ask, okay, is this the sister algebra of a, is it the graph of a functional graph? Okay, it depends on which one you choose. Okay, but now there is a less trivial example, which is given by multi-chamber quantum spheres. Here you have a special vertex with a loop and a number of other vertices, say k other vertices, and there is an arrow from the loop to each one of these, from the special vertex to each one of the others. Okay, this is not really a functional graph, but is the transpose of the function. Here you have that every vertex receives at most one. And this is actually what I'm interested in, not the functional graph, but the transpose of the function. And we will see why I mentioned this later. Okay, so the third part is this mysterious problem which has something to do with K theory. Okay, and then let's start from the beginning.
Once upon a time, in 1960, there was a paper by Etia and Todd where they computed the K-theory ring of complex projective space, and they found that this ring for CPN, where n is greater or equal than 1, this is the ring of truncated polynomials, zeta of x over xn plus 1, and x here is 1 minus the class of a line bundle. This line bundle you can define in several ways. For example, if you like the vibration from the sphere as to n plus 1 to CPN, this is the bundle associated to the basic representation of the one. Okay, so if you start from this ring structure of K0, I'm not mentioning K1 because K1 is 0 for CPN, is 0 for all the sister algebras that I'm going to mention that are AF sister algebras. So K1 is just 0. Let's pretend it doesn't exist. From K0, from this ring structure, you can derive some identities that are satisfied by the K-theory classes of a line bound. I'm not writing down these identities, just write what it means that xn plus 1 is equal to 0 in terms of the class of L1 and of the powers of this bundle, and that's it. And you write down these identities. Okay, now the surprising thing, I mean, it was not obvious that the similar identities hold also for CPNQ. If you put a Q, still these similar. I mean, you still have the analog of these line bundles. They are given by modules that are finitely generated and projective as one-sided modules. So define a K-theory class in the K0 of this sister algebra, and you have the same identities with the same coefficients that you have class. And this is in a paper of Francesca, Simon, and Gianni already 10 years ago, but we are still thinking about it. We are still understanding
the geometry behind this. So now the point is that in the classical case, you can say, okay, these identities are a consequence, are a manifestation of the ring structure of K-theory. For a non-commutative sister algebra, K-theory is only a zeta module or a group, a billion group. Is in general not a ring. On the other hand, there are several things that you can do. For example, you could say, okay, but if I find a star homomorphism from A tensor A to A, where A is my sister algebra, well, this star homomorphism induces a multiplication on K0A. So you turn K0A into a ring. So my naive question, but there are less naive questions I will mention soon related to what we are doing with Tomek and Piotr, but my naive question was if we can find a star homomorphism like this, when A is the sister algebra of CP and Q, such that the induced ring structure is what we want, is truncated polynomial. It was naive, this question, but I mean, there are things that you can do around this. Something interesting can be said about this. So classically, the ring structure is induced by the multiplication map. The multiplication map is a star homomorphism if and only A is commutative. A is a unital sister algebra. Okay. Now it's naive, this question, but not completely, because if you have an AF algebra, then there is a result that says that, and I'm being sloppy, I will not say what is here in parentheses, but the claim is that if you have a ring structure on K0A, then it must be induced by a star homomorphism. This is not true, it's not any ring structure. A good ring structure with some problem.
Which tensor product do you take?
Minimal. But these are all, I guess, all nuclear.
Yes,
Okay, so now I'm showing you what is this. I want to mention our two preprints with Piotr and Tomek.
Oh, I found the type.
Yeah. Where in Tomek last name now?
No,
okay, sorry. Yes. Okay, there is one preprint where these identities were proved again using groupoid sister algebra. See, the original proof was using index theory. This is kind of a side result. I would say this paper in this is not about this, but it is a nice side result. And the point is that the proof with groupoids, you can repeat it almost verbatim without changing any word for another class of quantum projective spaces that are called multi-Poolbeck quantum projective spaces. And in that case, that is a new result. I mean, it is something we could not do with index theory. So another thing that I want to mention is another preprint with Tomek, where here the question is different. It's not just, okay, let me find the star homomorphism giving the correct ring structure for CPN, but can we find a better K-theory functor which maps not to abelian groups, but to rings for sister algebras. And okay, but I'm not going to say anything about this. If you want, you can check the preprint. It's still a work in progress. So there is a version 1 is on archive. And I think we are working on version maybe 17, which is the next 16 are only on Dropbox, so you cannot see them. So, okay, but still version 1 will give you a good idea of what we are talking about. I hope Tomek is not complaining, making gestures that I cannot see.
No, his video is off.
Okay.
Okay.
Okay, so but here is just my naive question is this: star homomorphism inducing this ring structure. Okay, so let's start from the geometric construction where you have a compact out of space X. How do you get this star homomorphism? You start from, you have three ingredients. You have that the C of X tensor C of X is isomorphic to C of X cross X, where here you have the Cartesian product. You have that a diagonal embedding of X into the Cartesian product. And you have that C is the contravariant functor, is the result that you have a contravariant functor. With these three ingredients, what you do, you compose now the first, so the diagonal embedding by Poolbeck gives you a map from C of X cross X to C of X. You compose with the isomorphism at point 1, and you get your morphism from the algebra, tensor the algebra to the algebra itself, which is just the multiplication map. and gives you the ring structure of K-theory when you have a commutative system. Okay, this is very geometric. So can we do something? When we don't have a geometric space, when we have a non-commutative sister algebra? So can we generalize these three ingredients to a class of compact quantum spaces? For which class of compact quantum spaces does the diagonal exist? This is a very vague question. It means for which class of quantum spaces I have something like the ingredient that point to whatever it means. And what about ZP and Q? And unfortunately, we will see. I mean, the answer to these three questions, none is completely satisfactory, but still is something. I think there is some interesting ideas that led, not much, but still the ideas were interesting. Okay. So can we find a diagonal in the Cartesian product of two copies of a quantum space? So let's try with graph sister algebras. Instead of a compact Hausdorff space, I take a graph E. And then I wonder, well, first ingredient, C star of V tensor C star of V is not isomorphic to C star of V plus C. Because the left-hand side in general is not even a graph sister algebra, it's a higher rank graph sister algebra. So it is clear that in general these two cannot be the same.
But what do you mean by the Cartesian product of graphs? Because it means graph to graph, typically.
No, it means here that you take Cartesian product of objects and of vertices and of arrows, and the source and targets are defined in the obvious way.
Okay, that's not how one does it. Okay.
Yeah, but this is what I found also in the literature. There is something about this. So there are people who study also for ultragraphs the relation between these two algebras, and the one is inside the other. The one on the right is inside the one on the left, under some conditions.
There's a very nice elementary and fully developed theory for higher rank graphs. There is a concept of a Cartesian product among higher rank graphs. So if you have a Cartesian product of a graph of rank K with a graph of rank L, it will give you.
But here I want isomorphism,
I know.
so you cannot tell.
Sure, you get the graph of rank K plus L. And this exactly corresponds on the nose to the tensor product of higher rank graph sister algebra.
Okay. So the diagonal embedding second ingredient still exists. You can embed diagonally a graph in a graph Cartesian product with itself. And the third ingredient, well, this association of a graph algebra to graph is not a contravariant functor in a naive way. Okay, next. Okay, this is 2 out of 3 ingredients failed. But CPMQ is the sister algebra, is a graph sister algebra, but is also the core of a bigger graph sister algebra, which is the graph sister algebra giving other dimensional spheres. So let's forget about the sister of V and look at the and for
I don't get what you said on the first one. So is there actually like a more complicated product?
Yes.
So that will actually have the
Yes.
but it's a higher rank.
Higher rank. Yes.
Yeah.
I mean, it's very natural. I saw it in Kansas as a bait for physics.
And what was the question? Sorry.
The question was about what I was explaining, that if you have higher rank graphs, okay, so if you want arrows have colors, and the length of a path is an element in some power of natural numbers, then there is a very, very natural construction of a Cartesian product. So monoidal structure among higher rank graphs, if you
Which
want.
correspond to the tensor product of the system.
Exactly, because one of the biggest caveats of graph sister algebra is that this is a class which is definitely, except for trivial cases, not closed under the tensor product. Okay, so typically the tensor product of two graph sister algebras is not a graph system. Typically, of course, there are many exceptions, but this is completely remedied by higher rank graphs.
But here the Cartesian product is in the sense of sets.
Yes.
And what is surprising is that if you look at how this works, so if you take a sister EU1, tensor sister EU1, this is isomorphic to sister of E plus E EU1. I don't know if somebody observed this. I mean, you need something. It should be refined with no sinks. but it's very elementary. It is a very elementary fact, and you have this isomorphism. I mean, I was quite happy when I saw this because I thought, okay,
I've never seen it before.
one ingredient out of three is done. So ingredient number one works. Okay. The second, you still have diagonal embedding. And three, well, you get a contravariant factor if you restrict to admissible or cap admissible species.
Yes.
Now here the diagonal embedding is injective, so I don't care about it's the same. I can use admissible or cap admissible. So I can remind the people in the audience, cap admissible, which is one which is easy to define, just means that if you take the vertices in the image of the map and you look at the one that are not in the image, this is a hereditary unsaturated subset.
I also have to have this edge condition that you have to kill all the edges that end.
Yeah, okay, yeah.
It's not follows from
yeah, this is true, yeah. You have two conditions that imply also that it's hereditary unsaturated. Okay, so anyway, yeah, and you get the contravariant factor to U1 sister algebras. In particular, it means that if the diagonal embedding is admissible, you get a map from C star E cross E U1 to C star E U1. So you get your homomorphism, what you wanted. Well, this is very nice. Okay, now when is the diagonal embedding admissible? So this is, I mean, from a geometric point of view, you would say, okay, which one of these graph sister algebra have a diagonal of this quantum space is okay. The precise question now is, okay, for what graphs this is admissible?
Just let me make the sanity check. We have plenty of time, 24 minutes.
Okay.
If you take this Cartesian product of graphs, so take the Cartesian product of edges and the Cartesian product of vertices,
yeah,
and then you just take the Cartesian product of S and the source and target nodes, right?
Yeah.
Okay.
Yeah.
And this way it's again a directed graph.
Yeah. Oh. Okay, so the questions are, so first of all, the isomorphism at point one is only for graphs with no sinks. So for example, what about multi-chamber quantum spheres? Yeah. Can we do something with sinks? Okay, for CPNQ doesn't matter, but still is an interesting question. Second point, when is the diagonal embedding admissible for what he? And I have to say, all the answers to these three questions are not very satisfactory. Last question is, okay, maybe I don't have to use the diagonal embedding. Maybe I can find the other inclusion of graphs from E to E plus E that are admissible.
So you have an interesting reversal of the situations. Typically, it's the audience who asks questions and the speaker answers.
I ask a question and people answer. Because I have answers which are not very good answers, so maybe the audience has better answers. Okay, but let's start with sinks. So with sinks, at the beginning I thought, okay, maybe it's not really a problem because I have a sister algebra A. I want to turn a K star of A into a ring, but K star of A only depends on the Morita equivalence class of A. So I replace A by any other Morita equivalent sister algebra, and it's fine. And now for graph sister algebra, we know that given any graph E, I can find a graph F with no sinks, actually a regular graph, such that C star of E is Morita equivalent to C star of F. The case here is the same of these two, so we want to say, okay, replace just E by F, and you solved the problem of sinks. Okay, let's think about...
wait. And you don't need any assumptions like, well, finite or...
well, I mean, in my case, they are finite graphs.
I know.
With no infinite emitters. So the only problem is really the sink.
I understand, but I'm asking you what's really the status of this
green
and top for...
Yeah, I wrote it down, but not in the slide, so I can tell you maybe later. I don't remember. Okay, so I think that if it is rho finite, the desingularization is just adding a tail, both to sinks and infinite emitters. But if it is not rho finite, maybe you need also these branching vertices. Breaking. Yeah, so you need something lower. Okay, so in particular, if V0 is a sink of E, then to desingularize it, you just add an infinite tail, which is, is what you see on the screen. You have countably many vertices, each one connected to the one. And in this way, you no longer have things, and what you get is a more equivalent of what you have.
And these vertices V1 to infinity are not in graph E.
Are not new. Are new vertices, and you add this tail and you desingularize this.
So you blow up vertices, you blow up the projection set of
Yeah.
the compact operator.
So this is very nice. Now the point is that I'm not really interested in the graph sister algebra, but in the core.
In the core, yes.
Now the core sister EU1 is a corner in sister U1, but not a full core. And you can show this is something that you can prove. It's not difficult. I mean, it's not difficult in the Rofanet case. I don't even consider the non-Rofanet case. And but you can just check. I mean, there is a very simple example that I explain what's happening. Take E, the graph of 2 times 2 matrices, the vertices and one arrow, desingularize it, and you get the graph of compact operator. Now, what is the F core? Here, the core is C2.
So what do you mean sequence vanish again infinity?
Sequences of complex numbers is a C infinity, those who vanish. It's a diagonal compact operator.
Sorry, that's the 6 points above. Right?
Yes, it is a diagonal compact operator, right?
Yes.
And so clearly, I mean, since they are commutative, if they were more equivalent, they should be isomorphic, which they are not. Okay, so this idea already failed, unfortunately. You cannot, I mean, things are a problem. It's not something that you can easily remove because, again, because we are looking at the core of the graph sister algebra, not the graph system.
But you should mention that the C star of F before take U1 is as compact operators.
Yes, okay. Yeah. C star of F here is compact operator, C star of E is that. And those are more equivalent.
Exactly.
Is the cause.
Exactly, because yes.
Okay. So, second question, when is the diagonal embedding admissible? Well, you can prove that it is admissible if and only if the graph E transposed becomes a functional graph. So it means that in E, each vertex receives at most one, either 0 or 1. So what are examples of this kind of graphs? Well, multi-chamber quantum two spheres are examples.
What do you mean by transposed?
The transposed of a graph means that source enter the map.
So the opposite graph. Okay.
Yeah. I'm using again, I'm not sure if it is good, the graph theory terminology, which is not exactly the graph sister algebra. But okay, multi-chamber quantum two spheres belong to this class of example. Each vertex has at most one incoming edge, but also what are called arborescences, so directed rooted trees, like the black one on the left without the red arrow, but also the one on the left with the red arrow. If you have a directed rooted tree, you add an arrow going to the root, then it's fine. Still, it is in this class of graphs. And also cycle graphs, they are good, okay, fine. What is not an example is the graph of another dimensional quantum sphere, okay, which is one I was interested in, but okay, fine. Still, there are a number of examples. Now, what is the plot twist? The plot twist is that for every such a graph, the core is commutative. So sister EU1 is commutative. It is the diagonal subalgebra, sometimes it's called the Cartan subalgebra, so you can check what it is in Reborn book. Right? So this doesn't give you much. It gives you a ring structure on the case theory of commutative
Yeah, exactly.
Which we have already because it's a functions on a topological space. So you don't get something new. But to prove that you don't get something new is not easy. I mean, it's the proof of a negative result, which still is a result. Okay. So is there a loophole? So what can we do more? So suppose your graph E has a loop, L0, and call W0 the source of this, which is also the range. Then you can define another embedding of E in E cross E. You send every vertex V in the pair W0V. You send every edge E in the pair L0E, and still this is fine. Since L0 is a loop, yes, this is the morphism of graphs, and it works only because it is a loop. Okay, fine. Then when is this? I call this vertical embedding because it's a kind of vertical embedding of as a vertical slice of a topological space in the Cartesian product. You can have
just that it's morphisms of graphs, which is so funny. I just explained it. And I just explained it. Morphisms of graphs.
Yeah, it's an ordinary morphism.
But you don't know if it's admissible.
No, I know when it is admissible, not always, of course. Okay, first of all, you can have the horizontal version where you put L0 in the second slot.
Yes.
It doesn't change much.
Mhm.
So when is it admissible? It is admissible if and only if the only arrow, incoming arrow in W0 is the loop. So inside W0, you don't need any other arrow. Incoming arrow. Okay, still is not that bad because, for example, it works for other dimensional
Yes.
quantum sphere, where here you take not the last loop, the one that is streamable. You take the first loop.
Yeah.
The less streamable one.
Yeah.
It works for multi-chamber quantum to sphere where you take the loop on top.
Mhm.
It works for quantum length spaces. So it works for quite a lot of graphs. And now why, where is the catch? Why now the answer is not satisfactory? Now the answer is not satisfactory because you get a ring structure in K0, but not an interesting one. So imagine that you take a topological space and you put it as a vertical slice in X cross X. Then what is the structure? There is structure in K0 induced by the opposite morphism of star algebra, which is just multiplication by the integers.
Yes.
By the rank, you take a pair of vector bundle, the class of the set, and you multiply by the rank of the first.
Instead of getting the tensor product.
Yeah. Also is a non-commutative ring. So it is of course not a truncated ring. But okay, unfortunately, this is the best I could do, but I'm happy to, if anybody has any other idea. Okay, so this is the end. I put the archive number just in case the slides will be online, so in case somebody wants to check something, and thank you very much.
Thank you so much. Okay, normally I would ask, are there any questions, but now let me ask, are there any answers?
Yeah.
How about the room?
No, no.
You are an expert on graphics characters. Okay, Tomek, Adam, go ahead. Fire at will.
I don't have any questions.
Tomek, unmute yourself.
If I can add some comment.
Yeah.
So the main theme of our common paper with Francesco, this of at least 17 versions, okay, is the construction of some generalized diagonal. So the idea of our diagonal is that it should be something like a graph of the action in the classical case, and then extended to.
Oh, it falls.
No, it is disconnected. Oh, this is a cliffhanger for the movies, right?
So one possibility which is not explored
Tomek,
here
Tomek,
would be adding some
Tomek, your internet connection is not very good.
Okay, try again, unmute, try again, because you
Okay.
froze and then you vanished.
Okay, can you hear me?
Now we can hear you and we can see you, yes.
Very good. So one possibility one could try in this situation is to consider not a diagonal in the strict sense, but for instance, allow some twist between tensor factors on the left-hand side. Because if you want to create a homomorphism of associative algebras, then you have go from the fourth tensor power of A to the second tensor power of A. And typically, to define the multiplication on the tensor square of an algebra, people apply flip to the middle two tensor factors.
Yes.
But you can twist this symmetry between for this middle tensor factors And under some assumptions, you can obtain a homomorphism. Okay. So did you try to check this possibility?
So I thought about it.
For instance, in a braided case. In the braided case.
The algebra factorization structure.
Yes, exactly.
Yes.
But the point is that, I mean, to get a morphism in K-theory multiplication, well, you really need something from the A tensor array standard one way, right? Because then you use that K-theory of A tensor array goes to
The Kinef formula.
Yeah, the Kinef formula. That is only works with a standard tensor product of algebra. So if you change that, you cannot construct the multiplication in K-theory. There is a missing piece. Because I was not showing how you get the multiplication, but it's not just this map. This map gives you a map from K0 of A tensor A to K0 of A.
No, multiplication is, of course, twisted by this factorization data.
Yeah,
and this is associative multiplication.
Yeah, but the Punnett formula works with the standard.
Yeah. But if this, but if this is invertible, then you could define something. It's a matter of adding some algebraic conditions for this factorization data.
Yeah, maybe the in Punnett formula, maybe you get a twist or something like that.
Yeah.
It's possible. Yeah.
But wait, guys. So are you implying that such a theorem is done by somebody proved Punnett formula for?
No. It's a part of the project because, okay, among such factorization systems, you could consider ones which are trivial twistings. So for the purpose of so this is something like a cocycle condition and a coboundary condition. And for Punnett formula, maybe something of the form of coboundary condition would work. And for the multiplication for this twisted diagonal map, you have to use some compatible cocycle condition. It's a long shot, but there are some algebraic possibilities.
Yeah,
that's for
which will be split in two preprints because
a
reproduction by how it's called when one becomes two, which already happened.
Bifurcation.
Yeah, but yeah, mitosis.
Yeah, mitosis. Yeah. Okay, very good.
Okay.
So, Mike, anything else? Go ahead. We have plenty of time.
You have to go for 35 minutes.
No. 8 minutes is enough.
Okay.
Okay, so could you come back to this page with this course from?
But the definition, you mean?
No. Course of this graph sister algebras and product of graphs.
Yeah. This one.
Yes. So this is the first square after let's try again.
Yeah.
Okay. So this is some operation which is not related only to the product, because the product is on the level of graphs defining these graph sister algebras, and then you have an operation of taking invariants.
Yeah. But there is canonical gain on any graph.
Yes. Although it relates the Cartesian product of graphs with a tensor product of something, but on both sides you have different quotients. Okay, because you have an operation of taking the invariants of this E. So you have two copies of invariants. On the right hand side, you have one invariant.
But that's why it works, because without the U1...
Yes, I know this is necessary. But the interpretation of this as a kind of a compatibility between the product of graphs and the tensor product of corresponding sister algebras is slightly misleading.
Yeah, I agree. Let me write it down what you just said. So you can speak and I will be writing.
Because what would be it literally? It would be that some embedding from this first square, which is crossed in red, it becomes an isomorphism after passing to U1 invariance. But it is not so in this in the last case.
No, it's not so. It's not that. It's more complicated.
It's more complicated, yes.
You work directly with the AF4, you have a generating set, and then you show that there is a map on this generating set, which is projective.
Yes.
Yeah, it's diagonal. It's diagonal, all right, but you see, these are completely different spaces.
Yeah, but for topological spaces, this is great. It's only for graphs, of course. Yeah,
it's for graphs, of course.
But this is what I meant. I just want to.
Yes, but ideology Piotr sketched here for quotients of spaces is not so far from my idea of my comment.
Yeah.
Of course, the Cartesian product of graphs is more complicated than of spaces.
Yeah.
But definitely one copy of G is missing in this picture.
Well, but you are taking Cartesian product of the graph, not of this AF core, but of a bigger algebra. So the graph geometrically is not your space; it's something bigger.
I understand, but it's hard to say what is this object corresponding to this what you are taking square of.
But you see, if you take this Cartesian product, I mean,
yes. But the idea is to define kind of a diagonal.
I know.
Object. But the problem is what in this case it is this object.
No, but also, okay, if I may add another comment, of course, this diagonal embedding is of E in E cross E, but the E described by bigger space, not your A5. So it's not really, it's a bit cheating calling it the analogy with the classical case.
But you didn't let me finish. I wanted to say that if you would take this circle here, this Cartesian product in the category of higher rank graphs, okay, then the gauge action would not be the action of the circle, be the action of the two thoughts.
Precisely.
And this copy would appear. Okay.
Yeah. So making this comment, I had Piotr's explanation of higher rank graphs in mind.
So we have to study higher rank graphs.
Yeah, well, it's in our new project, so we
Yeah.
Or we have to give them on the patch. So cut this part from the registration.
Okay. Anybody else has any questions? No. So Francesco, because I'm, as you can imagine, very excited by such things. Would you somehow show me why this is true? I mean, I'm interested in this result saying when the diagonal embedding is actually admissible. So can you prove that this condition really does the job? What's the argument?
Yes.
Just let me clear my drawings. Yes.
Okay. Now something happened with this line. Okay. Well, I mean, this is I don't know if I remember now exactly, but it's really a simple argument with the graphs. You just have to check these two conditions, that if something has a range in the image, then the target is in the image. Then the arrow is in the image. I don't remember the conditions, so I have to see them again. But it's something that you check really easily. It's not complicated. It's like 4 lines of proof.
And here you say that for these graphs it works. It works for you say it works for rooted trees.
Yeah, I don't know why I can. Okay, I can move this again.
So it works for rooted trees, but it also works for something slightly more general, like you have an arrow going back to the root.
The root cycle graphs. You have multi-chamber quantum spheres. You don't have quantum spheres. So, for example, for Polish, the equatorial Polish sphere is that.
for category formless is fine. Because
it's a multi-chamber contribution.
of course, yeah, it's a one chamber. Okay, so that's by this condition of having a functional graph. Okay, okay. So this Ali has a question. Go ahead. Just unmute yourself. Ali, unmute yourself. You are muted.
You can unmute me.
Yeah, you can never unmute people on Zoom. Ali, unmute yourself. We do not hear you. You are muted.
Yes, yes. I'm sorry. Thank you very much for your very interesting talk. My question is, you indicated to the diagonal problem, and the problem you mentioned was motivated by the K-theory of CPN, the ring of truncated polynomial Z of X over Xn plus 1.
Yeah.
And you search for a diagonal map which induced the ring structure of the K-theory, the zero K-theory. But in reality, we realize that that's not only the K-theory of the projective space, but it is the cohomology of, for example, the singular cohomology or Doram cohomology of the projective space. So is it a reasonable question to think about the same question you mentioned about the CS algebra by replacing the K-theory by some kind of a cohomology, for example,
Yeah, cyclic.
Yes, for example, Durham cyclic cohomology. Is it reasonable to ask to the same question, but replacement of K-theory with some appropriate cohomology?
Yeah, I mean, I think it is a very good question, but I think that it is the same problem because let me show again. Here, all what we need, what is it? So we need this map, I don't know why, what happened, from A tensor A to A, and then functoriality of our cohomology to get the ring structure. So if you have this map, then whenever your cohomology is a covariant functor, like K-theory or any other kind of generalized, I would say, homology maybe, because you want covariant, right? Any kind of generalized homology would work. It would become a ring.
Yes, I see.
You get for free a ring structure on any on any functorial kind of, yeah, on a real homology, just because by functoriality.
Yes, yes.
And at the same time, you don't get theory. Yeah.
Yes. Okay, thank you for your talk.
All right, if there are no further answers or questions or comments, let's wind it up. I can see any volunteers. So let's thank Francesco again for a very exciting talk. Thank you so much. Let me start the recording.